right, welcome everyone. Today we're taking Chapter 12 of your 10th Standard Science syllabus and basically transforming it into a fast-paced, level-by-level masterclass. We're talking all about the magnetic effects of electric current. Now, if you've ever found yourself staring at your textbook, just completely lost in this maze of right-hand rules, left-hand rules, and wild circuit diagrams, you are in the exact right place. We're going to decode the whole shebang right here, right now in this explainer. So let me ask you a question. What actually happens when you mix electricity and magnets? Like, I want you to imagine a totally normal, everyday wire suddenly gaining the superpower to pull objects toward it, exactly like a magnet. Sounds kind of like magic, right? Well, a scientist named Hans Christian Ørsted accidentally discovered this very real magic when he noticed a compass needle just freaking out next to a wire that had current running through it. Okay, let's dive into this and see exactly how this invisible superpower works. Here's today's cheat sheet, our level up roadmap. 1. Electricity's secret superpower. 2. Shapes of magnetic fields. 3. Pushing wires, or magnetic force. And 4. Your home's electric shield. Stick with me and let's lock in those guaranteed board exam marks. All right, level 1, electricity's secret superpower, unlocking the invisible force. You know, electricity heats up your toaster, but here's the really interesting part. Any current-carrying wire magically behaves just like a bar magnet. To get this, we really need to understand what a magnetic field is. Think of a magnetic field as an invisible aura, or like a zone of power surrounding a magnet. If any magnetic material, let's say an iron nail, steps into this aura, the magnet gets to boss it around, pulling it in or pushing it away. And this exact same thing magically happens around our current-carrying wires too. Now, pay super close attention here because this is exactly what you need to memorize for your exams. CBSE absolutely loves asking for the properties of magnetic field lines. We draw these lines to visualize that invisible aura we just talked about. Outside the magnet, they always march out from the North Pole and enter the South Pole. Inside the magnet, they complete the loop, moving south to north. So they always form these continuous, closed curves. Oh, and here's a pro tip for you. Wherever you see these lines crowded closer together, the magnetic strength is way, way stronger. But why does this happen? That leads us straight into a classic exam trap. I want you to think about this like a mystery we need to solve. Why don't two magnetic field lines ever cross each other? Examiners love throwing this question at you just to test if you really understand what these lines actually represent.
The answer is wonderfully simple. See, a magnetic field line basically just shows the direction a compass needle would point. If two lines crossed, and you placed a tiny compass right at that exact intersection, the poor little needle would have to point in two different directions at the exact same time. And that is literally physically impossible. The needle can't split in half, right? So field lines never ever cross. Boom. Easy memory trick, guaranteed points.
Moving on to level 2, shapes of magnetic fields. Bending wires, bending rules. We know a straight wire acts like a magnet, but what happens when we start bending it? To figure out the shape, you need the ultimate cheat code, the right hand thumb rule. I want you to literally pause. Hold out your right hand right now. Yes, your right hand. Definitely don't use your left by accident. And do this with me. Imagine holding the wire. Point your thumb in the direction the electric current is flowing. Now look at how your fingers wrap around that imaginary wire. The curve of your fingers gives you the exact direction of the circular magnetic field lines. It is really that simple.
So how does this build when we change the shape of the conductor? For a straight wire, your fingers make perfect circles. So the pattern is concentric circles, and the key detail is that the field gets weaker as you move further away. But if you bend that straight wire into a circular loop, the circles of the magnetic field combine, and right in the dead center of the loop, the field lines become perfectly straight. And here is the secret hack. If you want a stronger magnet, just add more turns to your circular loop. It's like a multiplier. 5 turns literally means 5 times the magnetic power.
Which brings us to the ultimate boss shape of level 2, the solenoid. A solenoid is basically just a coil of many circular turns of insulated copper wire, wrapped up tightly into the shape of a cylinder. When current flows through it, the magnetic fields of all those loops add up. Outside, it looks exactly like the field of a normal bar magnet. But inside the solenoid, the field lines are perfectly straight and parallel. That means the magnetic field is uniform. It's equally strong at every single point inside. If you drop a piece of soft iron inside this energized solenoid, congratulations, you've just built yourself a super powerful electromagnet. All right, level 3, pushing wires, or magnetic force, when magnetic fields fight back. So far, we've seen electricity creating magnets. But what happens if you take a wire that already has current flowing through it and you put it inside an external magnetic field? Well, the magnetic fields fight back, and the wire actually gets physically pushed. The absolutely crucial point here is knowing how strong that push will be. And the golden rule? The force is at its maximum when the electric current and the magnetic field are at exactly a 90-degree angle to each other. If they're perfectly perpendicular, that wire is going to get shoved with maximum strength. If you change the direction of the current, the force flips. Change the direction of the magnet, the force flips again. So how do we actually predict which way it's going to get pushed? Enter Fleming's left-hand rule. Go ahead and shake out your left hand. Stretch your thumb, forefinger, and middle finger out so they look kind of like the axes of a 3D graph, all perpendicular to each other. Here's how you use it. Your forefinger points to the magnetic field. Your middle finger points in the direction of the current. When you align those two, your thumb will automatically point in the direction of the physical force pushing the wire. Seriously, practice this physical shortcut. It's going to be your absolute best friend for direction questions on the exam. Now, red alert. Listen up, because here is a massive trap that catches so many students. Sometimes an exam question won't just say current, it'll say an electron is moving to the right. Remember, electrons are negatively charged. The direction of electric current is always taken as the exact opposite of electron flow. So if an electron moves right, your current is actually moving left. You've got to point your middle finger left. However, if a positively charged proton moves right, the current is also moving right. Basically, always use the actual current direction for your hand rules. Fantastic. Let's transition to our final level, Level 4, your home's electric shield, real-life survival skills. We're going to apply all this science directly to the room you're sitting in right now. How does the electricity actually get to your devices safely? Let's start with a big, bold number, 220. Specifically, 220 volts. In Indian domestic circuits, the potential difference between the live wire and the neutral wire is 220 volts, alternating at a frequency of 50 hertz. To put that into perspective, that is a massive, dangerous amount of power flowing right through the walls around you right now. To safely manage this, your house uses 3 specific types of wires. First, the live wire, which is usually covered in red insulation. That one brings the high voltage current directly into your home. Then, the neutral wire, usually black, which completes the circuit so the electricity can flow back out. But the real unsung hero here is the earth wire, wrapped in green. This wire is physically connected to a metal plate buried deep underground outside your house. If a metallic appliance, like, say, your fridge, malfunctions and current leaks onto its metal body, the green earth wire takes that dangerous current and safely dumps it directly into the ground, completely saving you from a severe electric shock. Now, even with good wiring, 2 really dangerous things can still happen in your home. Let's permanently clear up the confusion between them. First up, overloading. This is when you do something like plug an AC, a heavy heater, and a microwave all into a single socket. You end up demanding way too much current, the wires heat up way beyond their safe limit, and a fire can literally start. Then there's short-circuiting. This happens if the plastic insulation on your wires melts or gets damaged, and the red live wire physically touches the black neutral wire. The current surges massively because the resistance suddenly drops to 0. Both of these are incredibly dangerous fire hazards. So how do we stop our houses from burning down when overloading or a short circuit happens? Enter the ultimate bodyguard, the electric fuse. It's a simple device placed in series with your circuit. When that sudden, massive surge of dangerous current hits, the fuse wire heats up instantly. But instead of letting that fire-starting heat reach your expensive TV or fridge, the fuse literally melts itself. It completely snaps the circuit, stopping the flow of electricity dead in its tracks. It essentially sacrifices its own life to save your home. And just like that, you have completely conquered Chapter 12. But before we wrap up, I want to leave you with a quick challenge. Look around you right now. Find the nearest plugged-in device, your phone charger, your laptop cable, a lamp, whatever. Electricity is actively flowing through it right now. Based on everything we just covered today, could you hold up your right hand and predict the exact shape and direction of the invisible magnetic field wrapping around that wire right at this very second? Remember, science isn't just stuck in your textbook. It is literally powering the room around you. Keep observing, keep asking why, and I'll catch you in the next explainer.